Так, я прошу прощения. Тут была заморочка, потому что система как-то реагировала. Ну, хорошо. Давайте я по-русски уже буду сегодня говорить, может быть, в последний раз. Так.
А нас никто не слушает по-английски на YouTube?
На YouTube кто-то может слушать. Ну, хорошо, ну давайте я буду говорить по-английски. Okay.
А вы не знаете список студентов там, после того, как сейчас поменяли все это?
В списке студентов, кажется, есть англоговорящие люди. Ну, хорошо, ну давайте пусть будет, давайте я буду по-английски. Окей. Just a moment. So, okay, I need some to introduce some introductory material. So the Clifford algebra and quadratic space. So by the subject that I would like to tell you today is the how duality, but I need some preparation. So first of all, about the Clifford algebra. Maybe you know this, but nevertheless, I would like to remind you about this notion. So we can assume that K is a field, arbitrary, but the characteristic not equal to 2. But actually, I will need the complex field, but assume now that K is arbitrary. So what is a quadratic space? Quadratic space, this is a couple. V is a vector space over our base field, assume for definiteness, but it is finite dimensional. It's not very important, but we need only finite dimensional spaces. And F is a bilinear symmetric form on the space. So because the characteristic is not 2, this is essentially a quadratic form, hence the notion, hence this terminology quadratic space. And to this datum, we can associate an algebra, which for some reason I will denote in this way, plus. And it is defined as follows. Take the tensor algebra over our space V and take its quotient. We have to impose the relations of such a type where V and W are arbitrary vectors from V. And after factorization over these relations, we get some associative algebra, which is by definition a Clifford algebra A+. So example, the trivial example is there is in fact no form, the form is 0. And then our algebra is simply the exterior algebra of the Grassmann algebra, which is the same. And returning to the general situation, note that our object is a filtered algebra. We have a natural filtration by proclaiming all vectors from V to have degree 1. So by definition, if you want to define the subspace of degree less or equal to some number m, sorry, this is, it's okay, it's okay. So this subspace is by definition the linear space, the linear space spanned by all monomials of length n, which is less or equal to m. But it's, by the very definition, it's easy to see that this filtration is compatible with the algebra structure. So we get indeed a filtered algebra. And we want to understand the size of this algebra. And to do this, as usual, we form the associated graded algebra, which is associated to this filtration. I recall the definition. So how to define a graded algebra? So by no, I don't have. So by definition, in the graded algebra, the component m is by definition the quotient. We take the subspace of degree less or equal to m and factorize by the subspace of degree less or equal to m minus 1. So this is just the definition of a graded algebra. And the proposition I have in mind says that the associated graded algebra for the Clifford algebra is canonically isomorphic to the Grassmann algebra, which is my notation, or the exterior algebra, which is the same. So the size, this means that the size of our algebra is the same as the size of a Grassmann algebra, because the filtered algebra and the associated graded algebra are, loosely speaking, of the same size.
Извините, а можно вопрос?
Да, конечно.
А вот меня просто смущает, если чуть-чуть вверх промотать, то, что мы берем оболочку векторов v1, vn, а не там просто, там, например, vi1, vn, то есть производим. Например, v2, v3...
А это не базис, это просто какие-то вектора. Абы какие вектора. Я не имел в виду, что эти вектора – это базис. Просто взяли какие-то вектора. Давайте запишем, если возникают такие.
Ну, то есть, например, v2, v3, например, для m равно двойке.
Нет, Свет, давайте поймем, что я имею в виду. Просто для любых какие-то v1, v2 и так далее.
Я поняла, да, хорошо.
Которые лежат в v. Просто так. Абы какие. Понятно теперь, да?
Да, все.
Чисто психологическое, так сказать. Вы спрашиваете всегда, если возникает такого рода вопрос. Ну вот, значит, что-то... Окей. So what I would like to say. So assume, take a subspace. So if this is a subspace, and take the restriction of our form to this subspace, and then the algebra, the Clifford algebra, which is related to this subspace, is a subalgebra of this algebra. How to prove this? What is evident? What is evident is that there is a row from this object to this object. This is by the very definition, because our object, the Clifford algebra, is something which is which can be called universal object. Universal object. If you wish, we can say that this correspondence, which assigns to any quadratic space the Clifford algebra, is a functor from the category of quadratic spaces to the category of associative algebra. So to any morphism of quadratic space, say morphism, one can say an embedding, it corresponds a morphism of Clifford algebras, but what is not evident at first glance is that it is subalgebra. I would like to, what I would like to emphasize, a little bit not evident fact is that this map is an embedding, it is injective. but because we can control the size of our objects, which amounts to the fact that if you take a subspace, then the corresponding Grassmann algebra is a subalgebra of the ambient Grassmann algebra. So this is essentially trivial. And in particular, if our subspace is isotropic, which means that our form is identically equal to 0, then this is a Grassmann algebra, which is a subalgebra, which contained here. Okay, so these are trivial remarks. Another trivial observation is as follows. If our space is finite dimensional of dimension n, then the dimension of a Clifford algebra is the dimension of a Grassmann algebra, and it is equal to this quantity. Okay. Now one can introduce some, I don't know how to say better, skew symmetric or anti-symmetric analog of a Clifford algebra. Sometimes probably it's called the Weil algebra, but I'm not sure that this is canonical terminology. So let's call it simply skew symmetric analog. So again, we take a vector space for our some arbitrary field and a form, but assume that it is anti-symmetric or skew symmetric. Skew symmetric by linear form, so it satisfies this, this relation. If you switch the variables, we get the minus sign. If this form is non-degenerate, it is called a symplectic form, and one can say that you have a symplectic space, but at the moment I don't want to suppose that the form is non-degenerate, arbitrary, but skew symmetric. And the definition of some algebra is quite similar. So we take the quotient of a tensor algebra, which is obtained by imposing the relations which are of the same type as before. But here we have a minus sign instead of plus sign as before. So hence this notation A minus instead of A plus. But the definition is quite similar, but the object is different, very different. Again, if our form is identically equal to 0, then we get not the exterior algebra, Grassmann algebra, but we get the symmetric algebra, because in this situation, the right-hand side is equal to 0, and our relation just means that our multiplication is commutative. So we get a free commutative algebra, which is the symmetric algebra. But this happens only in the trivial case when our form is 0. But what happens in general, again, we have a natural filtration, which is defined just as before by looking at monomials and imposing the a property that our vectors have degree 1, so we get filtration, and we can define the associated graded algebra, and it is canonically isomorphic to the symmetric algebra. So the size of our object is just the same as that of the symmetric algebra or the algebra of polynomials. In the number of variables is equal to the dimension of this space. Okay. Now I want to, so let's assume now that K is the field of complex numbers. And I want to discuss this algebra in more detail. So I want to show that it can be interpreted as the algebra of differential operators with polynomial coefficients. How to do this? So take the algebra first, take the algebra of polynomials in a given number of variables n, and define operators acting on this space, which I denote as m sub I and d sub I, m from multiplication and d from differentiation. So I will define two times n operators. And the definition is very simple. This is multiplication by a variable, and this is partial differentiation with respect to the same variables. And these are operators on this space, the space of polynomials. And this is my notation for the subalgebra of operators on the space of polynomials, which is generated by these operators m and d. And what we get? Here are the commutation relations. The m operators and the d operators commute, which is trivial, of course. And we have these commutation relation. The commutator between d and m is equal to 0 if the indices are different, distinct, and it is equal to 1 if they are the same. This is the Kronecker delta. And I recall here the definition of a commutator, just AB minus BA. The proposition claims that these are the defining relations of this algebra, because by the very definition, this is some algebra of operators, and these relations are obvious, but at first glance, it's not evident that there are no other relations. But the claim is that these relations suffice for the definition of this object. Let me give a proof. It is easy, but maybe I want to prove something. So take as V the space with a distinguished basis, E1, En, and some copy of these vectors, E1 prime, En prime. So this is a space of dimension 2 times n, and introduce a skew-symmetric form, in fact, a symplectic form on this space, by this condition that we have the value of the form on one vector from one collection and the other vector for a second collection is the Kronecker delta. And these quantities are equal to 0, which means, in other terms, that this is an isotropic subspace, and this is also an isotropic subspace, and actually they are Lagrangian subspace because they have maximal possible dimension equal to n. So we have two transversal Lagrangian subspaces and some pairing between them, which is given by this Kronecker delta. And by the very definition of our skew-symmetric analog of a Clifford algebra, you have a map. This is our universal object. And this is our concrete object. And the relations which I wrote here are precisely the relations in this universal object with respect to these bases. So we get this homomorphism of algebras, which sends these basis elements to the D operators, these elements to the M operators, and it is surjective, which is trivial. And our task is to show that there is no kernel here, so it's an isomorphism. And how to do this? Actually, we need to show that these objects informally are of the same size, and so this morphism must be an isomorphism. How to do this? So take arbitrary monomials which form a basis in our universal object. First of all, why is it a basis? We even don't need to prove that it is a basis. We only, it suffices to show that it suffices to show that these monomials span the whole algebra. And this is a kind of, this is a weak form of Poincaré-Birgeaud-Witt. The claim that these monomials span the whole algebra just follows from the form of the relations, because we can interchange any two letters and we get, which results in the appearance of some terms of lower degree. And by induction, we can reorder any monomial in this normal form. These elements commute, but these elements in general do not commute, but we can reorder any monomial and reduce it to this form. And the same can be done in our concrete object, the algebra of differential operators. And by the very definition, this monomial is sent to this monomial. So to prove that the both algebra are of the same size, it suffices to prove that these monomials, which we regard as differential operators, are linearly independent. And then it will imply that these monomials are also linearly independent. And so this will give us another proof of the fact that the size of this analog of a Clifford algebra, this skew symmetric Clifford algebra, is the same as that of a symmetric algebra. Okay? I didn't prove this, but in this concrete case, I can give the proof by looking at these monomials. So what we need to prove? So we consider any indices, any 2 times n indices, a1 and so on, up to bn, which are non-negative integers and arbitrary. And we want to prove that these operators are linearly independent. Okay, but this is what we need to prove. If we have some linear relation of such a type with certain complex coefficients, some finite linear combination, and if being applied to an arbitrary polynomial, if you get 0 for any polynomial f, this is only possible if all the coefficients are equal to 0. It's easy to prove. Just apply to this operator to some monomials and look what happens. So by induction, it's easy to prove step by step that all these coefficients are actually equal to 0. So this is the end of the proof. This is an exercise, if you wish, to prove this claim. I recall it. this proposition which is equivalent to saying that our algebra, which is defined, our algebra of differential operators, is just the same as skew-symmetric analog of a Clifford algebra in 2n variables with which corresponds to a symplectic form of a complex field. Okay. I'm sorry, just a moment. What next? Likewise, we can also introduce the Grassmann analog of this algebra as follows. We were dealing with polynomials, which is the same as the algebra, as the symmetric algebra over this space. But let's deal instead with the Grassmann algebra, or the exterior algebra, over the same space. So elements of this algebra, the elements are some wedge product, like this. So these are elements of a Grassmann algebra. And I define again the multiplication and differentiation operators, which are left multiplication and left differentiation. I already defined them, but I can repeat. So this is just the operator of the form. If you have some Grassmann element, we send it to this one. And to define the D operator, what is the D operator? We assume for simplicity that F is some monomial. And we look if there is our letters, if our letters enters this monomial. If it does not enter, then the result, sorry. Excuse me. If F does not contain Z I, then we set that DIF is equal to 0. And if it contains this letter, then we reorder our monomial in such a way that this letter appears in the front of our monomial, and then we just remove it. This is the result of application of this supply. Okay. Sorry, and these are the relations between the M, D, and this one, and these brackets is the anti-commutators, AB plus BA instead of minus. And look, these relations are very similar very similar to these relations. Just the bracket is different. Plus bracket instead of minus bracket. So a striking similarity. Okay. But the structure of the algebra is very different. So we have again the proposition of the same kind as before. So these are the defining relations. Okay. The equivalent formulation is as follows. Our algebra of Grassmann differential operators is naturally isomorphic to the universal algebra, which is assigned to quadratic spaces, A plus with V be the same space as before, and a similar form, but now it is assumed to be symmetric and not symplectic. So this is the definition. Again, these vectors span a Lagrangian subspace. Lagrangian maybe it's not a good terminology in the quadratic, in the case of symmetric form, but nevertheless it is isotropic, and this is also maximal isotropic. And some pairing between this collection and this correction given by this relation. And some remarks about these two kinds of algebras. In the plus case, in the Grassmann or Clifford case, this algebra is in fact the whole algebra of operators here. It's easy to see, just the same argument as before. Look what happens if we apply a monomial in the M and D operator to some Grassmann monomial, what we get. Actually, we can get all possible operators here, or just compare the size of the algebra, because the dimension of this algebra is just this one, which is, no, sorry, this one, which is just the dimension of the algebra of all operators on this finite dimensional space. In the minus case, the case of ordinary differential operators, it's not true. This is a proper subalgebra here, but nevertheless it is dense in this algebra. What means dense? The definition is as follows. Given an arbitrary operator on this space, and this is a countably dimensional space, so there are many, many operators, and the space of operators is very big, but for given an arbitrary operator and an arbitrary finite collection of vectors, which are polynomials, one can exhibit some operator from our subalgebra which acts on these polynomials exactly as this operator does. So one can say that it is dense in the strong operator topology. It's not a very good terminology because this is not a Hilbert space, not a Banach space. This is a countably dimensional space, but essentially this is the same as the strong operator topology. The next remark is as follows. In both cases, plus and minus, this operator is adjoint to this operator and vice versa. What means adjoint? Which is understood relative to a scalar product. So this infinite dimensional space and this finite dimensional space is equipped with a scalar product, which makes it a finite dimensional Hilbert space and an infinite dimensional pre-Hilbert space, not complete, but namely there is a non-degenerate positive scalar product. And this operator I joined in this sense. We can put this operator on the right and it becomes D, and vice versa. If you have here D, we can put it on the right, it becomes M. And what is the scalar product? Scalar product is defined from the condition that the monomials are orthogonal. So these are all possible monomials in the case of ordinary polynomials. These indices are non-negative integers. In the Grassmann case, these indices should be 0 or 1, and the product should be understood as the wedge product. So these are the Grassmann monomials. So the definition of a scalar product is that these and these are orthogonal, but we need also to specify the norm. And by definition, the norm is equal to 1. And in this case, the norm is equal to this quantity, the product of factorials. This is again an exercise to prove that if you introduce this scalar product, then the M and D operators are adjoint to each other. So I propose to do this, if you wish, to prove directly these three claims stated above. Some terminology, one can call this space of polynomials the boson-Fock space. Or maybe it's better to say some algebraic version, purely algebraic version of boson-Fock space, because it is a pre-Hilbert space, but it is not complete. If you complete it, then you get a true Fock space, a Hilbert space, and this is a finite dimensional Hilbert space. It can be called fermion-Fock space. Actually, there is a nice realization of this boson-Fock space, but maybe I will explain it in the very end. And the M operators can be called creation operators because application of M operators adds some extra letters. And after application of D operators, we get some letters are removed, are killed. So these are annihilation operators. And this algebra can be called the algebra of canonical commutation relations, CCR, canonical commutation relations. Again, this term is reserved for some completion, actually, of this algebra, but let's call it so, CCR. And the plus version is the algebra of canonical anti-commutation relations. The relations are here are just the relation between the M and D operators. So canonical relations, commutation, because here we have the ordinary commutations, and here we have the anti-commutation. And now I come to the main topic, which is the Roger-Howe duality. I will explain its boson version. So it's the explanation is a big long. So I begin to explain what will happen. Some general description. So this I will explain. I have to introduce a long list of data. So what we have? There is some compact classical group. We need some compact classical group. Actually, It will be orthogonal, unitary, or symplectic unitary group. Next, there is some classical complex Lie algebra. I will explain what it is. Next, we have a Fock space, a boson Fock space, with n, one can say, degrees of freedom. I will explain what is this n. Next, we need our algebra, the CCR algebra. This is my notation for the Fock space, and this is some subalgebra. I explained it. It is a dense subalgebra in the algebra of all operators on our Fock space. Here is some table. What is K? Orthogonal group, which is embedded into the unitary group, which in turn is embedded into the symplectic, compact symplectic group. In the second column, we have a Lie algebra, complex Lie algebra, which is symplectic. I don't want at the moment to write what is the rank of this algebra, but I would like only to notice that it is symplectic. It is GL, general linear, and orthogonal Lie algebra. So this orthogonal is skew-symmetric. Skew-symmetric matrices, arbitrary matrices, and some matrices which correspond to the symplectic Lie algebra. But here the inclusions are reverse. So this is a subgroup, this is bigger, and this is bigger. But this is smaller, and this is even smaller. There are some embeddings in the reverse direction here. Some author says that there is some seesaw pairs, kacheli in Russian. Okay, so here we have some object which is greater, and this is greater here. Okay, kacheli in Russian. Okay, this is the same here. Ножницы, one can say. Okay. So now I want to explain what is small n. It must be the product of two natural numbers, m is from here, and some n, which is related to the second column. And so our Fock space is the algebra of polynomials in the variables which are naturally indexed by two indices, a and I. A ranges from 1 to m, and I ranges from 1 to n. Next, what we have? We have, I will define it later, some unitary representation. This is my notation of the compact group on this Fock space. So this group, we have three cases, this one, and this one. And in each case, this group is represented by some unitary operators on our Fock space. I will explain later how to do that. Next, for the Lie algebra on the right, we have something similar, which means that we have some realization of our complex Lie algebras inside this algebra of differential operator, which means realization. This just an amorphism. So some linear map, in fact, an embedding of this vector space into this vector space, such that this embedding respects the Lie bracket here, which means that we have, take, so this, I need to, how to say, okay. relation as follows. What I mean by a realization, which means that on the right, we have a commutator in this object. Okay. And this realization is such that the elements of our Lie algebra are represented by certain quadratic expressions on our creation and annihilation operators, which will be explained again a bit later. So the generators of the algebra are represented by certain quadratic expressions in these operators. And by the general formalism, such a morphism of Lie algebras induces an algebra morphism of a universal enveloping algebra into this algebra, the algebra of differential operators with polynomial coefficients, which is embedded in the algebra of all operators on our Fock space. So one can say that our realization, to be explained later, determines some representation of G, or which is the same exactly of the universal enveloping algebra, some representation on this Fock space, and I will still denote it by the same symbol. And the claim, it's still imprecise because I did not define nothing, but I only continue to explain the general scheme. So the claim is that the operators which comes from the compact group and the operators which come from the Lie algebra, or equivalently from universal enveloping algebra, commute. And this means that our Fock space becomes a bimodule. There are two commuting actions, one by a group and one by some associative algebra or Lie algebra, and these two actions commute to each other. And the next claim is that the image of the universal enveloping algebra in this algebra of differential operators is precisely the commutant of our compact group. So what I mean here? Let's consider the subalgebra of this object, which consists of all elements script A of our algebra, which commute with all operators, which comes from our compact group. And the claim is that this subalgebra of invariance is the same as the image of our universal enveloping algebra. And from this claim, and from the fact that one probably needs to use also the fact that our algebra is dense. I'm sorry, I forgot if really we need this at this moment or not. But anyway, it's true that the following holds. Our bimodule, which we get from these two commuting actions, can be represented as a direct sum of some irreducible bimodules, which are of the form. Here, lambda ranges over some set of indices, actually some signatures, some positive signatures, because these are irreducible representations of the orthogonal group, and then we have positive signatures of a unitary group. Then we have some signatures of general type of a symplectic group. And again, lambda is some positive signature. So we have some set of irreducible representations which are coupled with some irreducible representations or module for the Lie algebra G. But these representations are finite dimensional. These are representations of a compact group, so and even unitary representations and irreducible unitary representations of a compact group are finite dimensional, but these modules are not finite dimensional, they are infinite dimensional. So these are certain infinite dimensional and irreducible representations of G, which is the same of a universal envelope algebra, but they are still highest weight representations. They are not finite dimensional, but nevertheless, they possess highest weight vectors. So they are weight modules. So they are of a form that there are highest weight vectors, and all the rest is obtained by applying some lowering operators, which acts from being applied to the highest weight vectors, which is a cyclic vector. One can obtain all the remaining weight vectors of our models, just as in the case of finite dimensional representations. So there are a lot of highest weight representations of complex Lie algebras, and irreducible ones are just the irreducible quotients of the Fermat modules. So these modules are some quotients, some proper quotients of the Fermat modules, which are on infinite dimensions. And what is also interesting, that these infinite dimensional modules are unitary or unitarizable, one can say, modules, but with respect not to a compact form, but to a certain non-compact real form of G, which just corresponds to the fact that they are infinite dimensional. And finally, I would like to make all this a bit more explicit, at least in the first case, when K is the orthogonal group. Then the corresponding Lie algebra is the symplectic Lie algebra, and N is just the parameter that I wrote before. So I need some explicit realization of this Lie algebra, symplectic Lie algebra, inside the GL algebra. So this is an algebra of matrices. So this is the algebra of all matrices of size 2n times 2n, and this is some proper subalgebra. How to define it? I need some explicit realization, some precise realization, which is obtained as follows. It's convenient to use this enumeration of the basis vectors using the -1 up to -n written in this direction, and from 1 to n written in this direction. And in the GLN, we have a matrix units where I and j are ±1 or up to ±n. But below, I will use I and j only. I will assume that I and j are only +1, 2, and up to n. So the basis, there is a convenient, for me, a convenient basis for a symplectic Lie algebra is as follows. So I assume that I and j are positive. Such matrix units, such some, and such ones. So what this means? This elements are of a form something here, some matrix unit here, and some matrix unit here. This is of this form, and these are from in this form. So what you have here, we have here some triangular decomposition. Triangular, or one can say grading. This is the 0 component. This is +1 component. This is -1 component. So our Lie algebra, which is symplectically algebra, can be written as the direct sum as a linear space, not as a Lie algebra, of G -1 plus G0 plus G1. Okay, and this decomposition is compatible with the Lie structure, which means that if you take the commutator, the bracket is compatible with the indices modulo 2. So if you take the Lie product of an element from -1 component and +1 component, we get some element from the 0 component, which is quite natural if you take some Lie commutator of element of such a type and such a type, we get something of such a type. In some equivalent formulation, the symplectically algebra is the algebra of the block matrices. And this is my notation for the transposition, but not the ordinary transposition, but the transposition with respect to this secondary diagonal. So this just means that if you want to understand what is this transposition. Okay, so no, I don't want to write this. Just forget this, okay? So the elements of this symplectically algebra are defined by the property that these blocks are related by taking this transposition and taking the minus sign, and these are symmetric with respect to this transposition, and this is also symmetric. And looking at this picture, we see that these elements are just symmetric. If you write them as matrices of size n by n, these elements are just represented by symmetric matrices, sorry, in this corner, okay? So all this is the basis in the symplectically algebra. And now some explicit formulas. We want to get some realization. So to each basis element, we want to assign some differential operators. And as I mentioned above, this is some quadratic expression. And so it's indeed some quadratic expression. The sum is of the A indices from 1 to m, and plus some extra scalar terms. So this is the Kronecker delta. So these extra terms appear only if I and j are the same. And times we need the factor of m and divide by 2. One can remark that this is exactly the same, all this is exactly the same as one can write the sum and 1/2 MAI. So in some more symmetric form, this expression call this expression, is the same as 1/2 of the anti-commutator of this. And this extra term appears from the commutator, from the commutation relations of these M and D operators. And here there is no problem, there is no extra term, just a quadratic expression in the D operators and minus similar quadratic expression in the M operators. And one can directly verify that this expression respect the commutation relation between this generator of a symplectically algebra. So we indeed get some realization, some concrete realization of this symplectically algebra by quadratic expressions in the M and D operators. And what next? And next we want to produce some representation of our compact group. How to define it? Very easy. We just collect only all our variables Z, A, I. We collect them, we arrange them into a matrix, capital Z, which is a matrix of size M times N. So this is some rectangular matrices of size M and N, which is filled with these variables. And our space of polynomials, which is our Fock space, is just the space of polynomials in this matrix variables, in this matrix variable, and in this notation, the action of an orthogonal matrix is just obtained as a change of variables. We need here to get some right action, and so we write here minus. We inverse, or one can write U transpose, which is the same for the orthogonal group. And it's easy to see, but just by looking at this picture, it's easy to see that this action commutes with the action of this area. So this is just because some hint is that this is some kind of scalar product. If you regard this, if you fix I and J, we get some two vectors. Some vectors, one is obtained from these quantities, viewed as vectors with A coordinates, and this is some other vectors, and this is just a scalar product, kind of scalar product. And it is invariant under this action. Under this action, so it's not proof, but just an indication of a proof. So this is some explicit description. And what happened next? I return to this table. So I try to explain this duality. We have a duality between the orthogonal group and some infinite dimensional representations of the symplectic group. Then we restrict this representation, which is actually called the Weil representation. Weil representation, or sometimes it's called oscillator representations or Weil representation, and so on. So we restrict this representation of a symplectic group to some subalgebra, which is isomorphic to GL, some smaller subalgebra. And when we restrict it, the symmetric group, one can say this is the symmetric group, group which generates the commutant, it becomes bigger, and it is the unitary group. And then one can still restrict to some subalgebra by adjusting some we need to rename this capital N in some way and define some subalgebra inside it, which is isomorphic to the orthogonal algebra. And by restricting, we get some smaller representations, which larger commutant, which is generated by the larger group, which is a symplectic group, which contains this group, some beautiful picture. And all this and much, much more is explained in the great paper, really great paper by Roger Howe. Here is the reference. This is a reference. Actually, this paper circulated as a preprint long before its publication. It appeared, I think, more than 10 years before. I repeat, this is a beautiful paper, and it contains not only what I tried to explain very briefly, but also some fermion version, which uses Clifford algebra, and actually some mixed version, some super version. We mix up the bosons and fermions, and we get some super algebra instead of Lie algebra. And actually, all this is called Howe duality or Howe correspondence, because we have some correspondence here. We have some correspondence, as in the case of Schur-Weil duality, correspondence between some compact group and some Lie algebras. But here the situation is more interesting, more complicated. This is some analog of a symmetric group, and this is some analog of a GL. And the duality that I explained before also can be written in terms of a creation and annihilation operators, but the difference is that the operators that the realization that I wrote before. So I would like to recall you what I did before. What I did before was related to the realization on the rectangular matrices with the action of GLM and GLN. Sometimes people also call it Howe duality, but this is a very simple version of duality, which was known long before Roger Howe. And the difference is that if you write these two commuting actions in terms of differential operators on the level of Lie algebras, you get first order operators. While in the Howe duality, we get second order operators, because here we have, I recall, we have second order operators. Second order operators. These are first order, of course, but these are second order operators. This is the difference. And as a result of more complicated picture in these formulas, you get infinite dimensional modules and not finite dimensional modules. You see that the action in this situation preserve the grading of the algebra of polynomials. And in the Howe duality, the action does not preserve the grading. And this explains why the modules are infinite dimensional. So this is a very important paper, which was the beginning of a very long story, and many, many papers were written in the sequel of this work by Roger Howe, because the Howe correspondence, some version of a Howe correspondence works not only in this situation, but in some, there are many variations, even for finite fields in p-adic fields. So this is a beautiful and a whole direction. And I can also indicate my paper, a long paper, which can be found. It is published in some book, but one can find it on my homepage. And if you want, we can look at it, and it contains some applications of the Howe duality to constructing unitary representations of certain infinite dimensional classical groups. Okay, so this is the end of the story. I want to close the stream.